Hello viewers, myself Dr. T. N. Oza here. Today I am going to present to you a new video based on spectral analysis. This video will be very helpful for you. First question is, what is called nuclear magnetic resonance technique? Give names of various NMR spectrometric techniques. So this has been defined in detail. The measurement of absorption of energy in the radio frequency region by a sample containing spinning nuclei when the latter is placed in an external magnetic field constitutes the realm of NMR spectrometry. Essentially speaking, this technique is quite similar to the other familiar absorption spectrometries like IR and UV, except that an external magnetic field is required to split the dormant nuclear quantum spin states into two I plus 1 components. The spectral data so obtained is plotted to give NMR spectrum, which is a two-dimensional graph display of the structural features of sample under study. The frequency of absorption or magnetic field is shown along abscissa x-axis, while intensity of absorption signals is shown along ordinate y-axis. Unlike the IR spectra and mass spectra, which produce very large number of signals, NMR spectra produce only expected number of signals, and the signals contain the structural features of the molecule. Looking into the details, certain nuclei possess intrinsic spin called spin quantum number, which is not zero, and associated spin angular momentum vector I, defined as h upon 2 pi multiplied by under root I plus 1. The spinning positive electrical charge of the nucleus causes it to behave as a teeny bar magnet of magnetic moment mu(n), which is directly proportional to the spin vector. In fact, mu(n) equal to gamma I, where gamma is called magnetogyric ratio, a characteristic of the nucleus. Thus, magnetogyric ratio of the nucleus is defined as mu(n) upon I, and it could be positive or negative depending on the characteristics of the nucleus. When such a spinning nucleus is placed in an external magnetic field, interaction between two vectors mu(n) and V0 takes place. The interaction energy is given by the dot product of both vectors mu(n) and V0. In this expression, the symbol Mi denotes the component spin number, of which a total 2I plus 1 are possible. Considering the component of I along the field axis, we can write EMI, that is energy equal to minus gamma Bz Mi h upon 2 pi. It may be noted that the component Iz equal to Mi h upon 2 pi equal to I cos theta, where the angle theta is the subtended by the spin vector I with the field axis, that is z axis, and mu z equal to gamma Mi h upon 2 pi. For spin half nuclei such as proton, Mi equal to plus half for the lower energy state and minus half for the upper energy state. Therefore, energy difference E negative half minus E plus half equal to delta E equal to h nu equal to negative gamma h Pz delta Mi upon 2 pi, which becomes equal to gamma h cross Pz, because delta Mi equal to minus 1. The resonance between the energy separation, that is gamma h cross Bz, and energy of radiation, that is h nu, results into absorption of energy by the spinning nucleus, leading to spin flip from plus half to minus half. This is called nuclear magnetic resonance absorption. Another way of looking at this phenomenon is in terms of Larmor precision of the nuclear magnetic moment about the field axis. Resonance condition is reached when the Larmor precision frequency mu L becomes equal to the frequency nu of the radiation. Now we talk about various NMR techniques. So many modern techniques have been developed. We will name few of them. First, continuous wave method, the traditional NMR method, using a constant frequency of about 4 to 1200 megahertz and accordingly varying magnetic field between 1 to 21 Tesla. It is more time consuming but cost effective and easy to maintain, hence is still quite popular. Second, Fourier transform NMR technique. The modern pulse technique. It uses microsecond pulses of radiation, thereby instantly exciting all the nuclei of the given type and following their free induction decay, which is displayed as a sine curve for each set of spin. For example, one such curve for methanol, two such curves for ethanol. The programmed computer online converts the time domain FID spectrum into usual frequency domain spectrum, with which we are familiar. The Fourier transformation spectrometers are very costly, very fast, and require liquid helium for cooling the solenoid magnet and liquid nitrogen to continuously absorb the evolving heat so as to save liquid helium losses from evaporation. Third is magnetic resonance imaging, which is used in medical field, which is preferred over CT scan because it uses less harmful radiations, whereas CT scan uses X-ray radiations. Fourth is attached proton test. Fifth is DEPT, distortionless enhancement by polarization transfer. Sixth is COSY, that is correlated spectrometry, the 2D technique. Similarly, we have head core. Another is inadequate. Another is totally correlated spectroscopy. So as I told earlier, so many newer modifications of NMR have been developed, over a dozen of them, depending on the suitability of the sample, etc. We should be very familiar with names of the most common ones. Now I read a second question. Which isotope of silicon has zero magnetic moment? Which has non-zero magnetic moment? In fact, silicon 30, the most common isotope, has no spin, hence NMR inactive. But silicon 29 has a spin of half, therefore it is NMR active, and NMR spectra of silicon compounds have been studied using this isotope. Third question reads, give examples of important spin half nuclei. What would be their shape? Spin half nuclei are proton, tritium, carbon 13, nitrogen 15, fluorine 19, silicon 29, phosphorus 31, tin 119, platinum 195, etc. These are spherical in shape and most suitable for NMR studies. Those nuclei whose spin number is other than half, they are quadrupolar and they are best suited for NQR studies, nuclear quadrupole resonance studies. Question 4. The NMR absorption signal for proton in MH, a hypothetical compound, is printed. Predict the spin quantum number of M. Answer. The multiplicity formula is 2Ni plus 1. where n is number of nucleus causing splitting. In this case it is 1. By putting the values of I and n, we get m equal to 5. On solving, we get I equal to 2. Note that the components of spin in the magnetic field will be plus minus 2, plus minus 1 and 0, and the 5 lines of the quintet signal will be of equal intensity because m is 1. Question number 5. 31p NMR of RCS2 whole twice PCl is multiplied due to the CS2 groups. Predict multiplicity m. We use the same formula, m equal to 2ni plus 1. I for phosphorus is half. It is being split by 4 protons. So 2 into 4 into half plus 1 equal to 5. Intensity distribution will be given by Pascal's triangle rule, 1, 4, 6, 4, 1. If hydrogen is replaced by deuterium, then the multiplicity will be 9 because for deuterium spin is 1. For hydrogen it is half. Sixth question reads like this. Some deuterated solvents still show proton NMR signals. Given below are the signal positions in delta ppm values along with their multiplicity or number of lines. Identify the impurity giving these signals. Some possible answers are provided for the viewers. CD3 twice CO. It gives a signal at 2.04, 5 lines. So the impurity is CH, D2, CO, CD3. Similarly, CD3CN gives a signal at 1.93 into 5 lines. The impurity is identified as CH, D2CN. CDCl3 gives signal at 7.26, 1 line. The impurity is identified as CHCl3. CD3 COOD, a signal at 11.53, 1 line, identified as CD3COOH. Another signal at 2.03, 5 lines, due to CHD2 COODRH. Paradioxane D8, a signal at 3.53, multiplet, identified due to C4H D7O2. So in this manner we can identify the impurities present in the spectroscopy grade solvents which are deuterated. The formula for calculation of MI where two different spins are involved is NS plus 1 multiplied by 2MD plus 1. Question number 7 reads, carbon 13 NMR data for some NMR solvents are given. Explain their origin and multiplicities. Data are in data ppm. CDCl3 77, triplet. CD3COD 49.0, septet, 21 lines, 21.5 Hz. CD3SOCD3 39.7, septet, 21 Hz. CD3 whole twice and DCO 30.1, septet, 21 Hz. 35.2, septet, 21 Hz. C6D6 128.0, triplet, 30 Hz. In this manner, a number of solvent data are given here, and we have to analyze the data. We have to assign the signals. So remember, deuterium has a spin of 1, and multiplicity formula we used in the earlier example has to be used to explain the multiplicity Briefly explain the features of a PMR spectrum. We must have looked into so many spectra. The noteworthy features are: first, a PMR spectrum is a 2D display of spectral data showing frequency of absorption along the x-axis, abscissa, and signal intensity along y-axis ordinate. The spectrum shows vertical NMR absorption signals. The number of signals is equal to the type of hydrogen chemical environments. The frequencies corresponding to the signals are field dependent. They are converted into delta ppm scale, which is universal, field independent. The more shielded hydrogen absorbed at higher fields towards TMS signal, whose delta ppm is arbitrarily set equal to 0, and less shielded ones absorb away from TMS signal. Some or all signals may be spin-spin coupled to proton, to fluorine, to phosphorus, hence a split. The splitting constant in J in Hertz units are field independent, but depend on geometrical variables of the molecule and the spin type. Line intensities follow predictable trends. The areas under the signals are in the ratio of number of absorbing nuclei in different sets. Sometimes spinning side bands appear in pairs. Splitting caused due to OH protons disappear on adding D2 or acid due to fast chemical exchange. A nearby quadrupolar nucleus such as boron or nitrogen 14 can broaden the signal of hydrogen. If solvent other than chloroform is taken, signal position needs to be corrected. Solvent correction. In some cases, low temperature may create difference due to dynamic effects. For example, at low temperature, proton signal of dimethyl formamide shows 2 methyl hydrogens as non-equivalent. At normal temperature, they become equivalent due to fast rotation about carbon-nitrogen bond. Hydrogen bonding and its type affect NMR spectrum, and they can be best studied using NMR. Another question is, draw hypothetical 1H NMR spectra of the following compounds: tertiary butyl benzene, 1,2-difluoropropane, RR prime C double bond CS2, acetone, acetaldehyde, methanol plus water, 1,2-dibromocyclobutane, 2,2,4-trimethylpentane, and ME3SiH. So this is for you to practice. Very simple examples have been taken. Question 10. Write about relaxation in NMR spectrometry. Relaxation in NMR is discussed under two headings, T2 and T1. In NMR, the net magnetization is detected in the XY plane, that is transverse plane, giving rise to free induction decay, FID spectrum with sine curve. The process by which the magnetization in the XY plane decays to its equilibrium position value of 0 is known as T2 relaxation or transverse relaxation or spin-spin relaxation. T1 relaxation is the process by which the net magnetization grows or returns to its initial maximum value parallel to the field axis. T1 relaxation is also called parallel relaxation or longitudinal relaxation or thermal relaxation. NMR relaxation measurements can be used for spectral assignment and study of quadrupolar and paramagnetic interactions and exchange dynamics. The delay of radio frequency induced NMR spin polarization is characterized in terms of two separate processes, each with their own time constants. One process called T1 is responsible for the loss of resonance intensity following pulse excitation. The other process called T2 characterizes the width of or broadness of the signal. In brief, the process of changing from an excited state to lower state or from the ground state by transferring energy to other atom or photon is called relaxation. T2 relaxation always proceeds at faster rate than T1 relaxation. Thus, the T1 relaxation time is always longer than or equal to T2 relaxation time. Another question is, 1H NMR spectrum of a compound shows two singlets, A and B, respectively separated from the TMS signal by 400 Hz and 700 Hz on a 300 MHz spectrometer. Calculate the chemical shift. What will be the separation of these peaks on a 500 MHz spectrometer? Very important calculation. We must be aware of such calculations. So delta A is calculated as 400 Hz divided by 300 MHz converted into Hz multiplied by 10 to the power 6, again multiplied by 10 to the power minus 6. If you solve it, it becomes 1.3 into 10 to the power minus 6. It is read as 1.3 ppm, ppm for 10 to the power minus 6. Similarly, 700 Hz divided by megahertz 300, it comes out to be 2.3 ppm. When the spectrometer frequency is 500 MHz, the separation delta nu A is 667 Hz, delta nu B is 1167 Hz. However, delta ppm values remain unchanged. That is the beauty of universal scale delta. Question number 12. 1H NMR spectrum of cumene, 1-methyl-ethyl benzene, or 2-phenyl propane shows 1:1 doublet at 1.24 delta, a septet at 2.28 delta, and a broad absorption peak between 7.02 to 7.34 ppm. The integration ratio is 6:1:5. Calculate the separation of these signals from TMS signal on a 90 MHz spectrometer. Very simple, very interesting calculation. Delta nu for CS3 is delta ppm into mu 0, that is 1.24 into 90 becomes 111.6 Hz. Similarly, delta nu CH 2.28 into 90 equal to 205.2 Hz. Delta nu C6H5 equal to 7.34 minus 7.20 divided by 2 into 90 equal to 644.4 Hz. Note it is a 6x spin system and 1 ppm is equivalent to 90 Hz. Another question reads, explain COSY NMR, NOSY NMR, APT and DEPT. They are very often asked as short notes and the concepts should be familiar. So let us discuss about them very brief. First is COSY. It is a 2D NMR technique which tells us which proton is coupled to which other proton. For this, spectra are shown on two mutually perpendicular axes and cross peaks meet on the diagonal. This method measures J coupling between protons, which may be 1, 2, 3 or sometimes 4 bonds apart. The advantage of COSY 45 degree is that the diagonal peaks are less pronounced, making it simpler to match cross peaks. Correlations appear when there is spin-spin splitting between protons. But where there is no splitting, no coupling, no correlation is expected to appear. For COSY, about 8 scans are required, tedious process. NOSY, or nuclear over Hauser effect. The NOSY spectra are distinct from COSY spectra, which use J coupling interactions between the protons up to 4 bonds apart. The NOSY spectra use through-space interactions, that is dipolar interactions, between protons which are not mutually connected by bonds, but are closely spaced via geometric constraints of the molecule. Thus, NOESY spectra identify the protons which are undergoing cross-relaxation and measure such rates, cross-relaxation rates. About APT, attached proton test. It is a 1D carbon-13 NMR technique. It is used to distinguish between various types of carbons. CHN, where N is equal to 3 methyl, 2 methylene, 1 methane, 0 are quaternary carbon. Methane CH and methyl CH, CH3. Their carbon signals are found upright, positive phase, while methylene and quaternary carbon signals appear inverted, downward, negative phase. Thus, APT helps in the assignment of carbon-13 NMR spectrum as compared to another technique known as DEPT. The APT is somewhat less sensitive, but it shows all four types of carbons, C, CH, CH2 and CH3 in a single run, whereas DEPT requires at least 3 runs and it does not retain the quaternary carbon as it has no hydrogen attached. After the initial pulse, spin vectors evolve differently for CHN. If the delay is set equal to 1 upon j, CH and CH3 vectors have opposite vectors compared to C and CH2 vectors. Therefore, the phase of CH and CH3 is 180 degree different from C and CH2 peaks. An improved version is called CRAPT, correlated APT, with compensation for variations in intensity. Now let us discuss DEPT, distortion-less enhancement by polarization transfer, is yet another 1D technique of carbon-13 analysis. It is routinely used to assign the absorption peaks of quaternary carbon because it is absent methane, methylene, and methyl carbons. The routine broadband proton decoupled carbon-13 NMR is first run, which shows all type of carbons, including the quaternary carbons. This is followed by variable proton pulses that is set to spin flip angle of 45 degree, 90 degree, and 135 degree in 3 separate experiments. As the name indicates, sensitivity is increased by polarization transfer from more sensitive 1s spin to less sensitive carbon-13 spin. The signal intensity at a particular time for each of 3 different pulses depends on the number of S atoms attached to the carbon. 0 for quaternary carbon, hence not detected. A separate subspectrum is recorded for each of the CH, CH2 and CH3 groups. The presentation of these 3 subspectra can be condensed to 2. Online DPT shows CH and CH3 upright, CH2 inverted down. The other line DPT 90 degree shows CH peaks up. The DPT 45 degree detects all protonated carbons, only protonated carbons as upright signals. The DEPT 90 shows only CH peaks. DEPT 135 shows signals of all protonated carbons, but CH and CH3 signals are upright while CH2 is inverted, downfield, negative phase. Question 14. An organic compound C9H10O2 gave 3 signals, 1.96, 5.00 and 7.22. What is it? So comparing the data from the standard tables, we can assign this to C6H5 CS2O COCH3, that is benzyl acetate. But we must have some idea of the chemical shift positions. For example, aromatic protons absorb around 7 ppm. The CH3 directly attached to CO absorbs around 2 ppm, and CH2 directly attached to oxygen absorbs at a still higher value, that is 5 ppm. Another question is assign delta ppm values of 6.2 and 6.8 to CH3, CH double bond CO CH3. It is a case of alpha beta unsaturated ketone. So resonance is possible. We have to write resonance structure which shows carbon number 4 is deshielded. So the lower value is for the shielded carbon, whereas the higher value is for the deshielded carbon. In this manner, we can assign the peaks. Question 16. For 1,3-dimethoxybenzene, arrange the ring of hydrogens in order of increasing delta ppm value. Answer is provided. Hydrogen at carbon 2 will have the higher delta ppm value, followed by hydrogen at carbon 4 or carbon 6, followed by carbon 5. Explain the estimation of keto-enol isomers using Ochen NMR method. Taking a simple example of acetyl acetone, we can write two tautomeric structures, CH3, CO, CH2, CO, CH3, and CH3, CO, CH double bond C, OH, CH3. So the method is we can measure the areas of CH2 and CH peaks. Alternatively, we can measure areas of CH3 peaks. One thing has to be remembered. In the enolic form, both CH3 are similarly to ring structure. So in keto form and in enolic form, the CH3 signals appear at different values. So by comparing the areas, we can determine the ratio of these two tautomers. Tautomerism has been extensively studied using NMR spectrometry. The last question is, what is a 2D NMR spectrum? One hypothetical example has been shown here. The data are plotted on two axes, which are mutually perpendicular. Thank you very much. Thank you so much.